Camera's all good?
Yeah.
Cool. All right, well, g'day everybody. So those of you who haven't met me yet, I'm Fraser. I recognise most of you. There's a bunch of here who weren't here last week. So we'll just do a little bit of recap and then we'll crack into the second phase of the meteorology briefing. But so just a bit of background on me. I'm a commercial pilot, fly airplanes for a job. I've been doing it for about 10 years for money and about 15 years for fun. Just shy of 5,000 flying hours in airplanes. And yeah, I've done a bit of instructing and various jobs around the place. Currently fly the Jetstar A320s between here, Australia and Auckland. Paragliding wise, I'm not the expert in the room. I've only been doing it a few years, but I identified pretty early in the piece that there was a bit of a lack of knowledge in the meteorology side of things. So I kind of put this together to help out the mob in Queenstown, and now that I'm here, I thought it's a good chance to present it to all of you. So this course, last time we went through, we did a whole lot of stuff about the science of things. Today's going to be a little less boring, hopefully. It's going to be a bit more relevant and a lot of introducing you to terms. So this whole entire thing was designed for a brand new PG2 student. So if you're well and truly past that, feel free to throw things in, get involved. I know a lot of things, I don't know everything, and a lot of you have experience to share, so feel free, stick your hand up, interrupt, do all those good things. I won't hold it against you. So, just to start it all off, I'm just going to go back to a couple of the slides last time. A few things that are fundamental to understanding weather are kind of important for the next phase as well. So, these are a list of 6 things that you can barely read because I have a terrible background on this PowerPoint. That are kind of fundamentals to understanding weather, and we're just going to have a quick little recap of them. So, the heat. Does someone in the room from last time want to tell me how important heat is to the weather? What does heat do in regards to weather? It heats things. Heat is everything. Take away from that first point is heat is everything. So if everything gets really cold, everything gets really still. If everything gets really hot, things start to move around, energy goes into the equation and things start to happen. Think about if you went to school, chemistry, energy is everything. The least energy, nothing happens. Lots of energy, lots of happens. The heat comes from the sun. Cool. Basic point 1. We're not going into heaps of detail today. Point number 2, temperature changes with height. Okay? So this is the biggest part of understanding how weather moves around, is understanding how temperature changes with height. So can anybody throw out what the name was for how air cooled with height? There was a term we used.
It's a lapse rate.
The lapse rate, that's right. So we referred to that last time. There was 2 different kinds of lapse rates. Environmental lapse rate. Amy about it. She was paying attention. Must have been sitting in the front row. So those 2 terms refer to 2 different kinds of air cooling. The first one being environmental. That is how air feels colder as you get higher. So you'll know it's warm at the surface, and as you get up the top of the mountain, it feels colder, and if you get going into space, it'll be freezing, right? So that's called the environmental lapse rate. Air feels colder as you get higher. And there's an average amount that air cools down. Anyone want to throw that out?
1 degree per 100 meters? 2 degrees?
Per 1,000 feet.
1,000 feet.
I'm a feet guy.
Okay. Sorry.
I don't.
Metric here.
Yeah, so a lot of you work in meters. I work in feet. Commercial aviation's all in feet. New Zealand does height in meters for mountains and stuff. Apologies that most of the stuff will be in feet. There's about 3 feet in every meter.
That's all right. So it'll be almost 3 degrees for
100 meters.
4,000 feet.
Something like that.
1,000 feet is 400 meters.
Yeah.
Round about.
Yeah. So air's on average about 2 degrees colder every 1,000 feet you go up, but in reality, air can get colder, it can warm up again. That's called an inversion. It can stay one temperature as you go up. That's an isotherm. So that's just the environmental lapse rate. That's how air gets colder, feels colder as you go up. Now, if air from the ground was lifted in a parcel and it rose, that air is going to cool at a different rate than the air that feels colder beside it. So say thermal's lifted up some air, or a mountain's lifted up some air, that's going to cool at a rate we call the adiabatic lapse rate. It's about 3 degrees every 1,000 feet you go up. So it cools down faster. If air is lifted as a parcel off the ground, it cools down faster than the air beside it that just feels colder as it goes higher. And then if it becomes cloud, it's going to occur at a temperature we call dew point. That's our third point. So dew point is the temperature that if air is cooled down to, it condenses into cloud. So say the temperature was 30 degrees and the dew point was 20 degrees, that air will rise and it will just look like clear air until it cools to about 20 degrees, and then clouds will start to come out of the air, the moisture starts to come out, that's the dew point. Any rising above that, the water will still continue to come out, but it will cool down slower. It cools at about 1.5 degrees per 1,000 feet. As that moisture starts to come out, energy comes out of the air with that moisture and it heats it a little bit. Doesn't heat it enough to cool the air, well actually heat the air up, but it just reduces the rate that it cools down. Hello?
Why does the adiabatic lapse rate cool down faster than the environmental?
So the environmental lapse rate isn't actually changing temperature, it's just the air feeling cooler.
But why does the adiabatic lapse rate, why is it so different?
Why is it different than the environment feeling cooler?
No, why does it go fast? Why does it cool down fast?
It cools down fast when it's dry, and that's the rate that it's cooling is just a amount that's based on the fact that as it gets higher, the pressure comes off it, because there's like all the atmosphere above us, right? Compressing all the air at the ground. As it gets higher, there's less air above it, so it expands a little bit. And just I'm not really great at teaching this exact why it's 3 degrees, but that air expanding, that energy gets spread out a bit further. It's going to feel colder. So that feeling colder as it goes higher happens, it cools down faster than just the natural air feeling cooler as you measure it at higher altitudes. So you've got to think about it. I have a slide for this. We're going to get back to this at the end. That one. So this is possibly hard to see. This is air feeling colder by 2 degrees every 1,000 feet. This is air that's rising as a bubble from the ground going up. It is just going to feel 3 degrees colder as it goes up because that air is expanding, and the mechanism making it feel colder is a different mechanism, and that just equates to 3 degrees colder. Hello?
Yeah, what do you mean when you say feeling colder as opposed to the actual temperature?
Yeah, so the environmental air is air that's not moving.
Right.
So it's just stationary air from here to space right now. It will feel 2 degrees colder as you measure it, as you go up. But if you grab this chunk of air off the bottom and then made it go higher, say it got pushed up a hillside by the wind, or it hit a hot object on the ground and it started making it rise, that bubble of air, that is still the same parcel of air closed off in a box, it will start to expand as it gets higher, like a balloon expands as it goes into space. That air temperature in that balloon will, as it expands, it will cool, and it cools at 3 degrees as that bubble rises, as opposed to the air that's still beside it, it wasn't interrupted, only feels 2 degrees colder on average. Hello?
I think the confusion is that you say it feels a certain temperature, but you really mean it is that.
Yes. So we just have to think about it as two separate things. Bubbles rising cool really fast, as opposed to the air that's just stationary will feel colder at each 1,000 foot higher. And once it's become cloud, it cools slower at about 1.5 degrees. If you want to go deep diving on that, I'm not the best person to ask. Jump on YouTube. YouTube is a great teacher.
Are you going to touch point why the hot air get released in the first place? It's just because the soil can't hold any more of that heat. The heat get released because the sun heats the ground, and that ground is specific.
like causing the air to be heated and things?
Yeah, well, when a thermal triggers, it's
Yeah.
because mostly the heat sitting in the ground just can't be stored anymore, so it has to go somewhere.
That's right. Yeah, we talked a little bit about that last time, about how the air is actually heated by the ground. And as opposed to being heated from the top down, it gets heated. The sun heats the ground. The sun doesn't heat the air, and the ground radiates that heat into the air above it. We are going to go a little bit into thermals as well tonight. So that's just a little bit of a recap. We're going to go into a whole lot of thermals and see them in place and how they all sort of develop over time. Wind is caused usually by a pressure difference. If you get high pressure somewhere and low pressure somewhere else, air flows like that from high pressure to low pressure. There's a bunch of effects on that. Coriolis effect we talked about last time. Coriolis effect is just that thing that makes all the air spin in circles instead of going a straight line. Like thermals, they spiral. You've seen your toilet flush, it spins down. That's the Coriolis effect causing that. Things like that affect the wind. And the last point, Bernoulli's theorem, basically broken down to a fine point that's relevant to all of you. As air gets squeezed through a gap, it will get faster. So you've got a valley, air goes into the valley. If it's going to get through a narrow point in the valley, it will go faster. If it goes over a hill, it will go faster over the top of the hill, just like a wing. Air gets accelerated over the top of a wing. That's how we create lift, because at the same time as it accelerates, there's a rule that means it drops its pressure, and there's the whole thing going on there. But that's just a quick little recap of what we did last time. Some of those things are going to be relevant tonight. You can ask questions as we go. But that was more sort of last time's briefing, which is on video, apparently available, possibly yet.
Not yet.
Not yet, but it will be available. We go into a whole lot of explaining all the little pieces of that puzzle. But now we're moving on to tonight's part, which is just a continuation of last week. Apologies for you that weren't here. Last time we talked about all the sciencey stuff. Now we're going to talk about a whole lot of terms and a whole lot of situations and things that happen in the air that are hopefully relative to all of you, so that you can either avoid them or use them, okay? So tonight's topic starts with turbulence and rotors. Has anybody not yet experienced turbulence? Not a single hand goes up. You all felt bumps, huh? Has anyone here had serious turbulence that they shouldn't have been in? Yeah, a couple grunts. Turbulence is one of the most dangerous things you'll probably find in the sky, okay?
Why is yours down? See, fly New Zealand.
So, what we've got here is just a bit of a diagram to try and make this visualise for you. There's another one as well on the next slide, goes into more detail, but what we're looking at here is a mountain with wind flowing over it. You'll see this wind, it flows along nicely, it comes up to the mountain. The air's going to nicely flow up the mountain. It doesn't look like turbulence yet, does it? At this point it's going to start accelerating, because remember, as air gets squeezed, air gets faster. You get to the top, this really fast moving air doesn't know where to go anymore. It's not being guided up a mountain. And just like you'd see in a river with water going over a rock, behind that rock, we get all of the turbulence. Turbulence is one of the most random things you'll ever find in the sky. If you can predict turbulence, you can make yourself a lot of money, because no one's managed to do it yet. All you can do is work out a sort of region it can happen in. Now, as a bit of a basic rule, turbulence can extend about 20 times the height of an object behind an object. So you get a little building like this. Now it's a one-story tall. Call that 3 or 4 metres. 20 times that way, for about 80 metres you're going to get turbulence off this building. If the air flows really slowly, it's not going to be very noticeable. If air goes really fast, it's going to go much more than 20 times the height of the object behind it. So, you've got a mountain What's the average height of a mountain in New Zealand? You don't want to throw a number out there? Meters? 6,000 feet? 2,000 meters? Sometimes they go higher, right? So 2,000 meters is 2 kilometers, right? What's that times 20? 40 kilometers behind these mountains, you can get turbulence. So you've all experienced the northwester. Everyone's talked about the northwester. The turbulence coming off the mountains that are a couple hundred kilometres that way will go a lot more than a couple hundred kilometres this way. So the biggest thing I want you to all take away from this is when there's wind and an object, you'll get turbulence behind it, and it can go a really long way. But there's something else that happens in turbulence, and we call it a rotor. A rotor looks a little bit like this. So that looks much more contrasted on my laptop. This is a mountain with snow on it. That was meant to appear blue. So the mountain just comes over like this, okay? So just like before, air's hitting the mountain, it's going up and over, and this is the turbulence zone, okay? But in that turbulence zone, sometimes the air's a little bit uniform, and it starts filling in on itself in these spirals. These little eddies, you could call them if they were in a river, or these rotors, we call them in the sky, they're big enough to invert a commercial airplane completely upside down in about a second flat. I've had it happen to me a couple of times flying behind hills on the way somewhere, and just out of nowhere you're upside down, you turn the controls all the other way and it takes forever to roll it back around. So if these things can turn an airplane upside down in a second, just take a second to think what that'll do to a paraglider. So I'm just trying to emphasize to you guys, turbulence is probably the most dangerous thing, or one of the most dangerous things you'll encounter. The biggest place you're going to find it, you want to throw out, where will you find turbulence? On the lee side, out of the wind behind an object, be it a hill, a tree, when you're coming into land, a building. These rotors will turn your wing inside out. Now, there's one other thing that a rotor does, and this is a big trap, and it's really easy to get into. Imagine you're standing on the lee side of this hill, but there's a rotor in front of you. You're not going to have turbulence, you're not going to have air flowing down the mountain. You can have air steadily in your face, blowing up the mountain. So say you've gone to the top of the mountain, and air's coming up this way, and you go, okay, well maybe you didn't go to the top of the mountain. You didn't know the wind was going this way, and you're slightly down it in the lee side. You're standing there and you go, oh, I've got a nice breeze in my face. You're standing there for 10 minutes. I've still got a nice breeze in my face. You take off. You're now in the middle of the rotor. You're now in the downdraft. And now you're in the turbulence. So these things are extremely deadly. And they're just something you really need to consider every time you go launching off a mountain. Now around here, you've all got a good forecast. We all know that if you're flying at Taylor's, the wind's generally going to be blowing off the sea. But when you're in the mountains, air can come from any direction as it weaves its way. So you just need to, if you're ever standing there on the top of a mountain, just think to yourself, is this a rotor or is this the actual wind?
How do you actually know about it? Just feeling like
You don't.
have access to any...
The best thing to do, if you're not sure if it's a rotor, go somewhere else, see if you've still got a headwind. So you can kind of pick what a rotor's coming off. If you've got a nice straight ridge line, it could just be the whole length of it. But if you've got a bit of a hill, so this is where this part comes in. Air could flow around the side of the hill and start coming in this way. So if you're in the middle of a hill and you've got a headwind and you're not sure if it's a rotor or not, you could go around the hill a little bit and see if there's any air coming in from the side. It's one way to do it, but this is, you're in the mountains, you're going to be walking. As you're walking up the mountain, as you're arriving on site, just take note of what the weather's been doing, things like that.
Watch for cloud movement.
Yeah.
If the clouds are moving this way, you have the wind coming up the slope, you're probably in the rotor.
Yeah, and remember how I said clouds form as air rises generally? if you're in an area where you've got a headwind but no clouds above you, that means that air above you might be descending. As air descends, it will make clouds go away, just as when it goes up, it helps them form.
I have a question. Sorry.
Yeah.
Maybe a bit stupid, but how do you tell the difference between a rotor on that side of the hill and an anabatic?
So anabatic wind is, we're going to cover anabatic shortly, but anabatic wind is air going up a hill, usually caused by heading on the hill. To tell the difference would probably be just covering enough area. You go, okay, am I in the sun? Is it likely to just be there's actually air flying up the hill as opposed to a rotor? You'd have to just kind of know your forecasts before you went out in the mountains. Go, should there even be wind on this side of the mountain? Anabatic wind can be formed over a hot surface. Am I over the top of trees? Are there a bunch of trees below me? You probably won't get much anabatic wind coming off trees. They're not going to heat up enough to make air come up the hill. But if you're standing on the summit, it's a rock, there's a whole lot of gravel below you, it's going to be almost impossible to go, is this anabatic wind or a rotor? It's just a bit of... This stuff can take a little bit of experience or just a bit of prior planning. If you're somewhere you didn't expect wind and there's wind in your face, I think it might be a rotor. This happens in Queenstown if you ever fly at Coronet Peak. Some days you're standing there at the launch at the base area, you've got wind in your face, but it's actually the northerly blowing over the top of Coronet Peak, wrapping back into your face. I've watched a couple of tandems take off out of there and get a whole lot of collapses as they frantically try and land out in the horse paddocks. This last little part here is just a bit of an awareness thing. Air can seem really calm on the front of an object when out from it it's flying really fast. So air stagnates on the leading edge of an object. So if you think about your wing, your leading edge of your wing has a big curve. Air builds up on the front of that wing and it starts to stagnate and it creates a little bit of a slow moving air with it. It's like it's pushing air along with it. And it can feel quite slow air. And as you fly out from it, you'll start getting the faster air current. It's just awareness that as you take off, you might find yourself in faster air, which is the opposite of what you think. Air hitting a hill will accelerate as it gets squeezed, so it'll accelerate at the top, but it might feel really sluggish down below. So just be aware, it might be a nice, okay, 20 kilometres an hour, and as you fly out from here, you might find yourself in much stronger wind than you anticipated. It's just another thing, but that one's probably less common because you're probably not taking off from these lower altitudes generally. But yeah, so there's just a whole lot of different things that are just really good that you all now hopefully know about to keep in your back of your mind. If you're ever taking off in the lee of anything, you might get these rotors, you might get turbulence. They're a really terrible place to be. And don't always trust a headwind, okay? Questions? Cool. So the next topic is just some bigger scale things that are happening in that same mountain range. So, same mountain, same airflow coming over. It does have nice straight lines down in this picture. There is likely to still be a few rotors in here. But this is something we call a mountain wave. Has anybody ever just looked up in Canterbury, looking towards the hill and just seen big rows across the sky of clouds, and then there's a gap and then another big row, and then another gap and another big row? These are called mountain waves. And what they're caused by is as air gets faster, as it gains altitude, it just causes these wave effects to happen. Now, for a paraglider, 50-50 whether this is going to be safe or not, depending on the speed of these clouds. But if you do see rows of these clouds, where the clouds are forming, there's going to be very fast wind. And as you get higher, it's going to be even faster. So you might look out and you go, oh, there's a nice cloud streak. There's usually rising air where I see clouds. Well, if you go to where that cloud streak is, you might find yourself in air that's so fast you're going to be flying backwards. These waves, when they form, so you'll see the areas where there's no cloud, that's where air is descending. And then when you see cloud, that's where the air is going back up again. It forms a little bit of a cap where it's raised. And then they're normally nice, smooth-looking clouds as they just go into a nice little ripple. And then it'll descend down the other side again. Now, the strength of these up and down drafts, does anyone want to have a guess how fast the air goes up and down in those ripples?
About 20 meters a second sometimes.
Yeah. 20 meters a second. Imagine going 3 stories up in a second and then just continuing up. So I've been in an aeroplane that I couldn't descend in an updraft of one of these. I had the aircraft at idle, I had it descending at maximum speed, and I had the rudder all the way into one side, so the aircraft was whacked out sideways, making a whole lot of drag. And I still went up. And I got taken from 3,000 feet to 9,000 feet before it stopped going up. And the only reason I stopped going up is because I travelled far enough downwind that I got into the downdraft again. So, how is that useful to all of you? Say you're flying at Taylor's. Someone's told you there might be a nor'wester, or you've looked at the forecast, there's a bit of a nor'wester coming through, but it's going to happen later in the day. If you look up and you start seeing these rows forming in the sky, it's just a bit of an indicator that that strong northwesterly wind is starting to blow over Canterbury, and that at some point after that, it'll start to arrive. I'm not saying if you're there, the nor'westerly is going to come in and you don't see it yet, that it's safe, but it's just an indicator, okay? So,
Comes like a flood day.
yeah.
Takes a wee while when it comes.
Yeah. So, he's talking about how we talk about the nor'wester touching down. Has anybody not heard that term yet? When the nor'wester touches down, look out for when the nor'wester touches down in the chat. That's these waves. We're down here at Taylor's Mistake, away from the Southern Alps. These waves will start to get bigger and bigger and bigger as the strong wind increases. Eventually they're going to start coming down and touching the ground. Initially on the tops of the ranges, they'll make their way down into Taylor's, and then who knows after that, you're hopefully not flying by that point. Any questions?
Fraser,
Hey.
what wind speeds are you talking about against this nor'wester touching down the wave?
I experience at about 30, 40 knots upwards, these things start to kick in the mountains.
Yeah, 100 plus k's.
Yeah. Exactly the right amount for Canterbury. I'd rely on some experience from somebody else to tell me exactly what speed they've experienced them kicking in. But they don't happen at slower speeds, they happen at higher speeds. And generally, if you look at apps like Windy, you can see on them if you change the altitude where the winds are being indicated from. If you see drastic indications of increases in wind with altitude, you'll start to see these forming at that same time. Generally ahead of a front. Anyone not know what a front is? So a front's that passing of a chunk of hot air moving over or a chunk of cold air moving over. As a front moves over, generally the wind in front of them increases and you'll start to get these effects. So yeah, if you see those rows in the clouds, in the sky, downwind of the mountains, don't think it's a great thing that's going to help you get lift. Consider, is this ridiculously strong wind? Do I want to be there? Or do I want to be flying when it arrives? Any other questions? Cool.
Are you going to mention that in lenticular clouds in the nor'wester as another indicator? Or?
Yeah, actually. We've got that in these. So I'll just jump forward to this now. This is in the cloud type, and this is particularly a dangerous cloud type. He just mentioned the word lenticular cloud. This is a lenticular cloud, just like a contact lens. It's a big curvy cloud. These will generally form in the mountain waves. They look like, they can be stacked like this, or they can be one nice pretty one. Sometimes it's just this part you see. But these are lenticular clouds. Those are what the clouds look like in these mountain waves. They also form on the mountains ahead of the mountain wave, and then you get the mountain waves after them. We'll come back to the cloud types and what's safe and what's dangerous shortly. This term here, orographic. Now, who in the room hasn't heard the word orographic before? Cool, this is good. Don't think into it too much. It's air lifted by the ground. is the simplest way to use the term orographic. You'll hear people use the word orographic cloud or orographic lifting. It just means the ground lifted it instead of something like heat. So air comes along, doing its own thing, it hits a mountain and it starts going up. Called it orographic lifting. You'll see that word come up quite a lot. Doesn't have too much practical purpose except just a type of lifting. So this is a bit of a what can happen as orographic lifting occurs. Air comes off the water usually in New Zealand. We've got water on that side, a little bit far that way and quite far that way. It's moist air, it's been sitting over the water. Air sitting over the water will become quite wet. And that thing I mentioned earlier, dew point, the temperature, if air is cooled down to dew point, it starts creating cloud. If it has more moisture in it, it happens at a higher temperature. Air at 20 degrees, if it sucks in water, it could condense at 25 degrees. If it sucks in more water, it'll condense at 30 degrees. So air that was 30 degrees, as it cools, it becomes cloud at a much earlier point. Anyway, cold air comes off the water, or wet air comes off the water, it pushes up onto, call it the west coast of the South Island. It's kind of a perfect scenario. And it starts getting orographically lifted up. It cools, it reaches dew point, it continues to lift and cool, and it's going to create a whole lot of cloud. If it keeps creating much cloud, it doesn't take much formation of cloud for that cloud to start raining and squeezing that water out onto the ground. That's why it's always raining on the west coast. When we get the easterly in Christchurch, like today we've got a big drizzly day, that's generally associated with that same effect, air coming off the Pacific over Canterbury, hits the mountains, get lifted a little bit, and then you start getting these widespread clouds on this side and a whole lot of drizzle that's with it. So that's orographic lifting. But with that, down the other side of the mountain, the air is now being squeezed dry or drier than it was. And as it descends, it forces it to dissipate the clouds. It warms back up. It sucks in any moisture that it had. And it warms back up at 3 degrees every 1,000 feet as that parcel descends down the other side. And it's warmer and drier on the other side. Now I've got a little bit of a maths breakdown on the next PowerPoint. But before I move into the maths side of this whole thing happening, does anyone have any questions about orographic lifting? One really relevant time you'll notice this effect is the last couple of times I've jumped on the chat and said it might be working down at Pendarvis Beach. A couple of people jump on there and go, it's been a bit wet and drizzly, I don't want to go. Well, this here is Pendarvis Beach. It's not usually raining. But you just go a little bit inland onto the main highway and the rain starts to form. That's because it's being lifted by the ground and causing the rain because of the easterly coming on. The same thing, it's the same reason it rains on the west coast of the South Island. If you're in the mountains on the west coast and it's pissing down with rain, you might find yourself standing in the sun at the beach because it hasn't lifted yet and caused the rain. So, for anyone who was here last week, this will be a little bit easier to understand. For those of you that don't follow along with this now, it's probably worth watching the video because I spent probably too long talking about this last week. But this is maths for what's happening for air moving over a mountain range, how it's cooling down, condensating, draining itself of air as such. So I mentioned that as air, if it's a parcel of air and it gets lifted, it's going to cool at 3 degrees every 1,000 feet. Eventually it's going to condense into cloud. Once it's in a cloud, how fast does that air cool down every 1,000 feet? 1.5 degrees, that's right. So this is the formula here. So imagine air's come off the water at 18 degrees. And the dew point, we call it, in this case, the condensation level, it's the same thing, is 9 degrees. So that means that it's about 50% relative humidity at the bottom. Half of that air is wet, but it needs to be cooled down by half its temperature before it's going to condensate. So 18 degrees hits a mountain. Every 1,000 feet it raises, it's going to drop in temperature For it to get to 9 degrees, it's going to take 3,000 feet. 3 times 3, 9. 8 drops down to 9 degrees. It's going to remain clear air until about 9 degrees, but at 9 degrees it's going to start squeezing out water. It can't hold it anymore. It's got too cold. As gas turns into a liquid, it also has to release some of the energy that it had when it was a gas, because it's being forced into liquid. It sheds the energy and the liquid together. Some of that energy goes back into the equation where it's trying to cool at 3 degrees, but that heat is slowing it down, so it's only going to cool at half the rate. 1.5 degrees every 1,000 feet it goes up. And it's going to continue to cool at 1.5 degrees every 1,000 feet until it gets to the top of that mountain. So if this mountain was 7,000 feet, it's got 4,000 feet to continue to cool. 1.5 times 4, 6 degrees colder. So from 9 to the top of the mountain, it's going to lose 6 degrees and be 3 degrees. Now, it's not going to get any colder than that because there's no longer any mechanism making it lift. It was being orographically lifted. That wind was hitting a mountain and the mountain is forcing it to lift. It's going to get to the top and just stop. As it starts descending down the other side, it's going to warm up at the exact same rate that it tried to cool. So air going down will increase at 3 degrees. Air that's in cloud as it descends will increase at 1.5 degrees every 1,000 feet. So say we're coming back down the other side. Eventually, the air will turn clear again and suck all the moisture back in. Now, as it raised, it squeezed a whole lot of rain out. That water's no longer in the air with it. So that dew point's going to be slightly cooler. Kind of backwards way to think about it. So it's going to descend a little bit. There's going to be a little bit of cloud on the lee side, but very quickly it's going to turn clear. And then from that height, where it turns clear, so in this case it only went down 1,000 feet before it sucked all the moisture back into itself. It's going to warm at 3 degrees every 1,000 feet it descends. For 6,000 feet, it's going to end up at 22.5 degrees. So the air on this side started at 18, made it all the way up and over, squeezed itself with all its moisture, started warming up really fast, really high, and ended up hotter on the other side. And that's why we get this effect we call the foam wind in Christchurch. Some places in the world call it Chinook wind. It's normally named after the mountain ranges it's coming off. You get these really hot, dry winds coming off the mountains in certain conditions. And that is why. It's this whole science and the maths of how air cools as it goes up and over and down the other side. Now, there's a whole lot more in this on the Met Service PDF handout. I did attach it to the chat last week. I can do it again if people want. There's a lot that goes into understanding a foam wind. But if you just remember, if you get any wind hitting any mountain where it makes a bit of cloud on the windward side, it's usually going to be warmer on the other side. And that's called the foam wind. You go all over the world and you'll experience this. Any questions about that before we move on? Cool. I think that's the last of the maths for the whole thing, hopefully. Anabatic and catabatic winds. We talked about this before. So someone who hasn't told us what anabatic or catabatic is, does anybody want to take a guess what, say, catabatic wind means?
Air going down.
Yes. And the opposite, anabatic, air going up.
Anabatic means building and kata means take apart. Anabolic and catabolic.
Yeah. It's good someone actually went to school and paid attention. So, anabatic wind is wind going up a hillside. Catabatic wind, air going down a hillside. There's a couple ways to remember this. One very PC way to remember it. Anna stood up, so the cat jumped down. Think of something really dirty associated. That's the best way to remember these things. But I just won't say it on camera. So an example of an anabatic wind being air going up a hillside is perfectly demonstrated in this picture here, where you've got the sun going into a valley. It heats up the sides of the valley walls. It might even heat up the air on the ground. And that air will try to flow up the hillside. Now, the reason it won't just go straight up is because the air can't lift off because there's nothing underneath it to replace it. It can't just suck dirt up. So it doesn't just lift straight up. It has to flow up the mountain along the side until it can at least get separated by air behind it. We'll go into triggers and things a little bit later for those of you who are already thinking about it when we get to the thermals part of this. Now, the opposite occurs in valleys at night time. So say you're literally here. How many of you haven't flown off the gondola yet? Cool, good bunch of you. So this whole basin here is exposed to the sun during the day. It'll get heated up and air will start to flow up the hillsides around the gondola. But when the sun goes away, that ground starts to radiate its heat into the air and the ground starts to cool down. Eventually that ground will feel colder than the air touching it, and it will cool the air touching it back down again, and then the air will start to flow down that mountain back down over the ground. So in the evenings, if you're flying right until sunset and you're landing down here at the cricket field, and you're up above and there's a nice breeze blowing towards the gondola, but just as you come into land, you notice that the windsock's facing the other way. Glenn did a great job of pointing this out last week. There was a really nice wind blowing up the valley, but as we're all coming into land, we're getting tailwinds. And that was this katabatic airflow flowing off the valley walls, down over the town and running out underneath the air. So we call that a katabatic flow, generally cold air. Another place those are really common are on top of glaciers. So if you're in the mountains, there's snow around you, there's a big glacier somewhere, that will be cooling down the air, and then you'll get a flow of air off it that's really cold flowing down the bottom of the valley. It moves completely different than the rest of the air away from the ground. Any questions about anabatic, katabatic winds, or does anyone have any experience with these they'd like to share, whether they're really helpful or really dangerous? Yeah, so the biggest takeaway is if you're exposed to the anabatic and katabatic flows, the air on the ground may be very different than the air around you while you're on approach, okay? Just like here, if you've got wind flowing up the valley, doesn't mean the wind on the ground will be going the same way. Cool.
Even tailors can be quite a trick, and when the temperatures are cooling down in the evening and it's still blowing easterly, and the katabatic wind will just be like 10 metres, the lowest 10 metres, so you can think you're coming to land into wind, but end up it's behind you, so
Yeah.
you can get caught up.
That's what always pays to try and land at the start of the field, because if you aim downwind and these katabatic winds take you, you might go through the trees. Right. Has anybody not heard of a sea breeze? Cool. Everybody's heard of a sea breeze. Does anyone not know what a sea breeze is? Right? No hands. Good. A sea breeze is just a cycle. You've got a hot piece of land heating up here during the day, generally the middle of the day into the middle of the afternoon, and it's going to make air rise. You've also got cold ocean air, a cold ocean surface, cooling down the air above it. Air will start to descend onto it as it gets cooled down, and it creates a closed circuit loop. And really, in real life, it's not as perfectly closed circuit as all these diagrams will teach you at school. But in the middle, between where the air's going up and going down, you get normally a nice breeze off the water. So that's why from about mid-morning until late afternoon, you'll get the sea breeze, which will quite often be opposite what the prevailing winds that day are. Now, up high, and now this can only be 1,000, 2,000, 3,000 feet. You'll get the air going in the opposite direction, finishing that loop. The extent that this flows inland will start just above the beach. When it begins as a very small loop. But as some of you who have progressed into flying in the mountains will experience, when that gets a chance to fully develop, it will make its way all the way into the middle of the Southern Alps. Those of you who have flown at Cheeseman, you'll get to a point in the middle of the day where the sea breeze arrives. So this can become a gigantic rotating engine that can have a whole lot of force to it. And it's characterized, one, by a cloud being sort of in a line sometimes a bit of an area of cloud that sort of gently makes its way inland. And that's sort of where the sea breeze is at that point. And then it'll go up, and then air above it will flow the other direction back out to sea, where it completes the loop again. So the sea breeze can do a few things to the air you're flying in if it arrives. So say we're in here, we're at Cheeseman. Cheeseman's somewhere the club goes quite often in that general area. The air was still. The air was having nice vertical thermals. They were pretty mellow. It was all nicely under control. Now those thermals were getting caused by a hot rock heating up some air, and it was rising. If a sea breeze arrives, the air mass that's getting heated is going to completely change. You're going to get either warmer air that's slid over the land, or cold air if it's being pulled in fast enough off the sea, and it's going to completely change what air is being heated by that rock. What it normally does is trigger all your thermals, and things get pretty explosive. So I haven't got a huge amount of experience flying in Cheeseman, but based on the talks, these guys have all experienced it. You're flying around, and all of a sudden the entire sky turns into a frying pan. It all starts boiling up like crazy. It's triggered by the sea breeze making its way inward. So being aware that this happens and looking for things like that cloud, that area of cloud moving in and over you, can be an indication of the sea breeze arriving. When it arrives, expect the environment you're flying in to change. Okay? What it actually does is like trying to play the lotto. Sea breezes will follow valleys, they'll go over hills, some places they'll flow the wrong way up a valley against the wind, they go all over the place, depending on how that sea breeze mixes with the prevailing air flows. It can work in your favour, but it can also just be dangerous for those of you who are expecting a nice day flying and then all of a sudden they go, whoa, everything's going crazy. So just to be aware, as the day goes on, the sea breeze will make its way inwards and it will start to affect your flying. Be aware of it. Be aware that it's not just as the day gets hotter, it's not just going to feel better. Eventually, things are going to change drastically. Some days this sea breeze will make its way only to the edge of the mountains. Some days it might not even get past the town. Some days the sea breeze off the west coast will meet the sea breeze off the east coast, and you'll get a giant row of clouds all the way down the Southern Alps. Land of the long white cloud. So that's the sea breeze. Any questions? Cool. Now I talked about when the wind from the west coast met the air from the east coast and made a big cloud. Well, on a big scale, that's called convergence. Convergence can happen on a big scale and a small scale. The word convergence is used a lot in paragliding. It's when two air masses collide, and then the air in the middle has nowhere to go but up, and you get lift. So say you're looking at Banks Peninsula. It's a nice calm day everywhere. The peninsula starts to warm up, all the way from here to Akaroa. It's going to pull air in from the sea, create that big sea breeze over the peninsula. Right down the middle of the peninsula, you're going to get convergence. So these pros who are much more talented than me will use that to fly really long ways out to Akaroa. So that's just a term. We're not going to deep dive into it too much. The word convergence just means two air masses colliding and going up. It could also be pulled in by the cloud itself. And I'll go into what I mean by that a little bit later, but basically a cloud can become so energized that it starts to pull its own air in. This is a characteristic of a thunderstorm, and we'll look at that just a little bit later. So that's convergence, two air masses colliding. They don't normally go down, they go up. Cool? And this is the part that I think everybody wanted to do. So hopefully I'll wake the rest of you up again. Thermals. Now, we're a coastal site here at Taylor's Estate. Soaring is the word generally used. Thermaling is another kind of flying. Has anybody not had a chance to thermal yet? Cool, a bunch here. So, thermaling is when you catch hot air that's rising up, as opposed to soaring where you're on the coast, on a cliff or something, you've got that air rising up a hill, creates a bit of lift. So we're going to go into basics and a little bit of an example of how thermals work. Learning to fly in thermals is a whole other thing. Best learned with somebody who knows what they're doing first. Going and discovering them on your own can bite you, but they're also fantastic for the sport. So this is a basic cycle of a thermal. And it starts here, in the middle. The air gets warmed by something that's hot on the ground. The air that's been heated will start to rise because it's hotter than the air beside it. It starts to go up. It will cool down as it rises, and eventually it will match the air beside it. At some point, a loop starts to form, or a loop can start to form, because as that air rose, it had to be replaced by something. It starts to pull air in from the sides. It goes up. The air at the top needs somewhere to go. It's not just going to continue into infinity because there's already other air up there, and it can form these loops. So the takeaway from this is generally a thermal goes up in the middle, and if it's really calm, on the outsides you'll get a little bit of a downdraft sometimes. Around the outside of a thermal, you'll get air flowing into it. And out the top of a thermal, it can start to sort of spill outwards a bit. This air on the outside is much more calm and slow than the air up the core. The next PowerPoint, we're going to break this down step by step. I got my PowerPoint skills out, but I was very bored and did one of these next things. So this is the sky, and this is the ground. The ground. So when you've got the air not blocked by the sun or anything, the sun's going to hit the ground. So we're going to have heat being added to the equation from the sun. Things are going to start to happen. The sun. Sun heats the ground. Now, the sun is heating up everything. The same amount of energy generally in the area, but some objects will heat up faster than other objects. Does anyone want to throw out some examples of things that heat up faster than, say, grass?
Dark field.
Dark fields,
rocks.
Yep. Tractors. Yes.
Rocks, buildings.
Yep.
Railway.
Yeah. Iron. The darker an object is, the more it'll heat up. Things like rocks will heat up, metal will heat up. Roofs of houses are metal, they're dark. Tennis courts. Things that are vegetation, things with a lot of moisture in them take a lot longer to heat up. So that's kind of the opposite. So rock, concrete, roof, those locations are going to heat up faster. In the mountains, you'll spot boulders, you'll spot rocky hillsides. In towns, you'll spot roofs, tennis courts. In the country, you might just spot roads. Roads will kick off thermals. Now, the air touching those rocks will heat up faster than the air above the grass. But it won't just heat up and release straight away. So do you remember I talked about how the air here feels 2 degrees colder every 1,000 feet it goes up? This air's been heated, but as soon as it starts to lift a little bit, it's going to cool down really fast at 3 degrees every 1,000 feet. So it's constantly being forced to feel colder than the air around it if it tries to lift initially. But eventually, after enough heating, that air is going to heat up a lot more, where it has the potential to lift away from the ground. And even though it's cooling fast, it still might feel warmer than the air around it for a while. Now, that bubble will release either by it getting so hot that it releases on its own, or it's disturbed. So this is where roads come in, car parks and things. If, say, you've got a really hot chunk of air sitting on a car park and a car drives through it, it's going to toss some of that air into the air. It's going to give it just a bit of a push. So that's something that works very well in Queenstown. If any of you ever fly there, there's a car park right next to it. If you're really struggling and you think you're going to sink out, just park yourself over the car park, wait for a car to leave, and quite often that'll trigger a thermal that'll take you back to the ridge. So there's your car. It's driven through the bubble and disturbed it, and it starts to flow upwards. Now, if the heat source is still pretty weak, this air is just going to lift in bubbles. Some of you might have experienced the thermals where you just get a little bit of a lift and then it stops. And then some of you might have experienced the other thermals where they just keep going. Well, when that source is weak, it's just going to start trying to lift in bubbles until that concrete rock roof gets hot enough that it can start really constantly providing heat to the air and pushing it upwards. Now, as that heat starts to rise, it needs to be replaced. So that's where we start getting this airflow coming in from the sides, and that's just air that's been sitting on the grass around it. It's not going to feel as warm, okay? So it's been mentioned a lot when there's thermals going on at Taylor's off the launch. Same happens at the gondola. When these thermals are going up, you can get a bit of a tailwind pulling behind you on launch, pulling towards the rocks just out from the launch site. That's this wind coming in to replace the air in the thermal. Now, that air replacing it will do one of two things. If this rock is really hot, it'll just keep heating this cold air up and sending it into the sky. And that's where you get the nice constant thermals off the hot source. The other thing that can happen is that cold air can cool that rock back down. So while it was stationary, it heated it up, it lifted, cold air came back in, but it's not getting heated fast enough that air can just cool that rock back down again until everything settles down. And that's where you'll get the bubbles of lift. Rock heats up, releases air, pulls more cold air in. It's like putting water on the rock, it cools it down. It'll eventually heat back up and do it again. So you get these thermic cycles. Is a word you might come across. And obviously cold air doesn't lift, the lift stops. Did anybody not follow along? Cool. So, just because we can, just a little recap. Sun's going to heat the hot objects. The air will start to heat a little bit. It won't rise initially.
Why doesn't it rise? Why does it form that bubble which sticks to the ground?
Yes, so there's a picture that's better to explain this. That one. So say the air on the ground over the grass everywhere was 26 degrees. This is the environmental lapse rate. So air not rising, just the air feeling cooler as you measure it as you go higher. It feels 2 degrees higher, 2 degrees cooler as you go up. Now, say the air on the ground, it's able to lift if it gets heated sufficiently, that as it starts to rise, it remains warmer than the air beside it. So this air is cooling at 3 degrees because it's a parcel of air lifting. But imagine if that air got lifted to 27 degrees. So it only got heated a little bit. It's only 1 degree colder. As it goes 1,000 foot higher, that 27 degrees air is going to feel 24 degrees, it's going to stop immediately.
Oh, right.
So that bubble needs to get sufficiently hot that it doesn't get immediately stopped from rising.
Oh, okay.
Cool?
Do you know how high? Sorry, I got no. Do you know how high those bubbles are?
No.
Right. Okay.
Everyone will be different.
Yeah.
Does anyone with experience want to answer how big these bubbles can get before they start getting kicked off?
Doesn't that also depend on the air pressure and the moisture in the air?
Yeah, and how hot the rock is, how widespread the rock is, how cold the air next to the rock is there wind? I don't have that answer for you, I'm afraid.
No worries.
Do you
It's not
need to
standard
wait
size.
for the bubble to get bigger and you can fly, or do you just rely on the
The lift needs to be lifting. So there could be a perfectly good thermal sitting in a car park ready to go, not releasing. And it's going to need something to go through it to kick it off. It can be a tractor driving through a field can kick it off, car in a car park, a little bit of wind, prevailing wind moving over it just to get it mixing to kick it off. Otherwise it can just get so hot that it kicks off, but you won't get any lift off a bubble that's just sitting there ready to go. Cool. So yeah, the bubble goes up, car or bubble gets hot, it starts to rise, cold air comes in to replace it. It either stalls it or that cold air allows it to become a constant thermal if the rock's hot enough.
Does the angle of a slope influence how, like, the release of these bubbles? Like, say if your slope's really flat or if your slope's really steep, is one more likely to have greater...
Yes. So this is where the katabatic and anabatic effect comes in. And we're going to have a look at why we refer to some of these things needing triggers. So flat objects will get hot and they'll form these little bubbles on top of them. If they're on a hill, you might find them trying to slide up the hill.
So there's more natural movement in that, like, there's more likely to shift, things is likely to shift off if there's already there.
If there's a hillside, yeah, you've got gravity affecting it as well.
Yeah.
So gravity might cause the air to slide down, shift over the rock, kick off the thermal. Bit of katabatic air up the hill might also just give it enough of a nudge to start flowing and kick off. So yeah, flat thermals will work differently to thermals on a
Is
hillside.
there like an ideal steepness for these to form? Like too steep, no good because the sun's not going to hit it, not too steep. Is there an ideal...
I imagine every single situation would be different depending on what it is and where it is. It'd be a case of just going and finding out, to be fair.
Like, depending on the season then and the angle of the sun onto the rock at a certain time of year, like would different slopes be better for different seasons?
Yeah, so there's something we call insolation. It's not in this PowerPoint, but I'll tell you about it. So insolation is about how the sun is spread over the ground. So imagine coming out of our sun here is our nice beam of sun. It's going to heat, it's going to put all of its energy into this tiny little spot. If the hill was on an angle like that, that same beam of energy hitting that hill is going to heat up that spot right there. Now imagine if this beam hit way down here. That little bit of sun, that one beam of sun, is going to be spread over this much wider area. We call that insolation, the spread of the sun. That's why the earth is heated. Well, it's cooler in the winter because the sun's coming in from an angle and it's spreading its energy out over the land over a much wider area, as opposed to the areas in the equator where all that energy is concentrated onto a smaller area. It's going to get much more heating. So when you get the hillside, like say this side of the gondola here where the rocks are getting heated by the sun in the evening, they're going to be much hotter than anything being heated on the ground where that sun's getting spread out a little further. Does that make sense? And that answers your question?
Yeah, it does.
Yeah. Insolation is the word. Direct sunlight will heat things better than spread sunlight. Cool. So this PowerPoint now we're going to look at some of these numbers as air rises and look at how we can get blue thermals, small clouds, or thermals that have really big clouds on top of them. So, as I mentioned before, this here was our environmental lapse rate. Now, on average, the environment cools by about 2 degrees per 1,000 feet. In reality, it does all sorts of crazy temperature shifts, but this is just the average one, and we use it to sort of demonstrate what's going on. So, like I mentioned before, we had a thermal, and it heated the air on top of that. Say we'll call it a tennis court, heated the air to 32 degrees. So the air around it feels like 26, but that air is being heated to 32 degrees. That thermal will cool as it rises. 3 degrees, I've asked you that a million times already tonight. As it 3 degrees every 1,000 feet, it goes up. And eventually, it will match the temperature of the environment around it. When it reaches that temperature where it matches, it's going to stop going up. It's no longer hotter or colder, so it's just going to stop rising. So in this example, it rose 1, 2, 3, 4, 5, 6,000 feet because it was 6 degrees warmer. Not much of a temperature change, goes pretty far. So the air starts rising. The air also starts cooling adiabatically. That's that 3 degrees per 1,000 feet. Eventually it will match the environment.
Can I just ask why environmental lapse rate is different to that 3 degrees per 1,000?
So this is just air that's not rising. This is just the air that's stationary around us. It will feel colder. If you were measuring it on the ground, it'll feel 26 degrees. If you go up 1,000 feet, it'll feel 2 degrees colder.
But why is that different to this?
So if you took this parcel of air here, take that as a box, and you put it here and you heat it, and you keep it in its box. Yeah. As it rises, it will expand as the air pressure reduces off it. As it goes up in altitude, it will expand because there's less atmosphere compressing it. That expansion effect will cool it down. And the rate that cools down is 3 degrees every 1,000 feet.
As opposed to there, where the pressure obviously is less as you get high.
Yes, so this is referring to air that is being lifted, and this is referring to the temperature of air that is stationary, just sitting here.
Yeah.
So it just feels warmer on the surface because air is heated from the ground up. Sun heats the ground heats the air. The air feels warm on the ground, and then it does feel colder as you go up because it's not being heated. And eventually it gets colder and colder and colder up into space. But if you were to take that parcel of air and lift it, it's forced to cool down as it expands, and that expansion makes that bubble inside the box here cool down really fast. So think about this as just...
it's a loss of latent heat.
Latent heat is, essentially, it's being, the amount of energy is still there, but it's now spread out really far. It's going to feel colder when you're measuring it. So this is about lifting air, the adiabatic lapse rate. Adiabatic refers to a closed parcel of air being lifted and cooling, as opposed to just air feeling colder as it was just sitting there as you go up higher and higher.
This might sound dumb, but do you know, I think I'm getting confused. So when you get to the top of a thermal thing and you've got the temperature matches and cools and stuff, are you always going to have cloud at the top of a thermal there?
Yes, not always, and that's what we're going to look at next as an example when the clouds form. Perfect, what do you call it, a segue? So imagine this air is only heated 1 degree warmer. When it gets to this height, it's going to be a little bit warmer. Now imagine, just for example, the dew point of this particular parcel of air is 15 degrees. So at 15 degrees, if it continues to cool, it's going to start forming cloud. It's still warmer than the air beside it, but only just. So it's going to go up a little bit more. It's going to form a cloud for a little bit. 1,000 foot lower, 1,000 foot higher, it's 13.5 degrees. Any higher, it's going to stop rising. So if it went up any more, it's going to be 11 degrees. It's going to be the same temperature and stop rising. So depending on how hot the air starts, determines whether it's going to get a cloud on the top of it or not. Because if it's hotter, it's going to get higher and higher and continue to cool. If it stops before it reaches dew point, it doesn't form a cloud. If it crosses dew point as it rises, it will form a cloud.
Oh, okay. So it has to be hotter to get past dew point, which you got you.
Yeah.
Okay, so
Clouds
cool.
only form a dew.
So
And dew point is...
in this example, it was only a little bit hotter, so we only got a little cloud before the temperature's still balanced out.
What sort of cloud it looks like? Is it like different sort of clouds? Or is it like...
Yes. Yes. That is... All seen these?
Yeah.
This is a cumulus cloud. This is the most common type of cloud to see on the top of a thermal, but it's not the only type of cloud you see on a thermal. We've got a whole cloud section after this. to have a whole classroom go, yes, it's such an achievement. So we're back here. Now, so 32 degrees, we got a nice high thermal, 6,000 feet. We went up only one more degree. It got high enough that it formed a bit of a cloud. Now, say we raise it just 2 more degrees, we're going to get a little bit of a runaway happen. So the air cools. It goes up to 17 degrees. About there, it decides it's hit its dew point. Cloud forms. So in this case, we've called dew point 14 degrees. It's now going to cool it at 1.5 degrees per 1,000 feet. That latent heat being released with the water is going to help slow down the cooling. And if we look across every 1,000 feet, those numbers are going to stay warmer than the environmental air. Because now the environment's cooling at 2 degrees, but that's only cooling at 1.5. It's going to continue to stay warmer because now the air around it's going to constantly feel colder than the air in the thermal. So if we 1.5 to 12.5, next to 10 degrees, it's still warmer. If another 1.5 degrees, 11, it's still warmer than the 8. And in fact, the difference is starting to grow. If we go all the way to the top, 2 degrees, -2. It's still 4 degrees warmer all the way at the top. The bigger this difference in temperature, the faster this thing is going to rise. So you can see now that we started at a sufficient temperature, we start to get a runaway. And as long as this remains hotter, and it starts to feel as if the difference starts to get greater, it's going to accelerate. The rate that air rises will be faster if it feels, say, 10 degrees warmer than the air around it, as opposed to if it only felt 1 degree warmer. If it was 1 degree warmer, it would only rise slowly. 10 degrees warmer, it's going to go really fast. So this is where I was talking about where air can actually start to suck in its own air, and then it becomes almost self-sustaining. So when you get that convergence I mentioned earlier, where the two airs combine and go up, well, they can also be pulled up like a vacuum by these big clouds. So you think that's somebody you want to be in a paraglider?
No.
Somewhere like this, excellent. You've got this big indicator going, oh, there's a thermal, there's a nice cloud on top of it, it's not going anywhere, it's going to be pretty benign. But if you see this, you might just be flying over here somewhere. Next thing you know, you're getting sucked that way, you're getting sucked that way, icicles start to form off your nose, you wake up in a tree. So, did anybody not follow along, or does anyone have any questions about that process? So it's all determined by how hot the air starts when it leaves the ground, will determine how high it can get. And when in reality, this becomes a big zigzaggy line. It doesn't work like that. Slide back to a PowerPoint from our first day.
And presumably how much moisture is in the air, and therefore...
Yes. So it's a good point. If the air was really moist, like it had just come off the ocean, it was really hot, you're in the tropics, dew point might be 29 degrees. That process might start all the way down here, and then it's got a really long runaway. The sooner it becomes cloud, the better chance it has of running away. If air's really dry, these clouds might not form until they're up here, they might not get the chance. Deserts, you might not get clouds until you're at 20,000 feet. Over the ocean, you might get them at 1,000 feet or lower. Yeah.
Do you get the leak above the clouds?
Above the clouds? Generally not. So, like, commercial aircraft will find themselves flying above these because the air has stopped going up. It's all smooth up here. This is where we park ourselves, where the air, about 36,000 feet generally, these things all stop, and you'll find them all flying up there. So, not normally. But if you were in an orographic situation or a mountain wave, the air might be rising up there, and you might get a little bit of moisture below because it might be a different parcel of air. So air mixes. It's like a traffic light. Has anyone been to Cobb & Co and had a traffic light? You've got the different oils. You might have air coming out of a valley. That air might be really moist because it's been soaking up some tree moisture. That air going up in the mountain wave might form a bit of cloud, but the air above it wasn't moist. And that air might dry out and not form clouds, but it might still be going up above the cloud. Yeah, a lot of crazy things happen in real life. So I've got a little bit of a picture somewhere here. This one. This is our RASP chart. This is all to tie it all together. RASP chart's a skew-T chart. This is basically a graph of how air is actually cooling as it goes up. There's a whole lot of reference lines here. They represent your environmental lapse rate, your adiabatic lapse rate, and your dry adiabatic, your saturated adiabatic lapse rates. So the red one here, that's your actual environmental lapse rate. That's what it's actually doing as it goes up in height. This is quite a steep, it's quite a shallow line. It's pretty constant as it goes up in height, as opposed to here, it's cooling down a little bit faster because it's sloped over. So this scale on the bottom is temperature. This scale vertically is altitude. And that's measuring how it cools down with altitude. This yellow line represents your dry adiabatic lapse rate. So as air cools down, and then the green line represents your saturated adiabatic lapse rate. So if your air was here, it started on the ground at about 15 degrees. Say it got warmed up by the sun, about 5 degrees to here. It's only going to raise a little bit because it's going to follow this guideline of the dry adiabatic lapse rate. It's going to cool down as it goes up until about this point, if it had a 5-degree head start when it left the ground. As opposed to over here, where the air cools down a little bit faster with altitude. If it got a 5-degree head start from 25 up to 30, it's going to run all the way up to here, which in this case was 12,000 feet, before it matched the temperature and stopped rising. Now say it got to about here and it hit dew point, turned into a cloud. It's going to follow the green line up, and it's never going to stop until it runs out of water and it returns back to the yellow line, and then it continues in. So this is a bit of a real life example. We're not going to deep dive into forecasts in real life tonight. This is just, I want to concentrate on a few just examples of what's actually out there. But this is just applying what we just saw. This little blue line is the humidity of that air. So in this example, it was a really bad day. The humidity met the temperature, there was cloud there, all the way up to here. Where the air became a little bit drier, the cloud might have stopped. Maybe a little bit more chance of a cloud here, and then it dries off again. And the same in case here. So it's dry on the ground. As it get higher and higher and higher, it get closer to its dew point. It didn't quite get it, and then it dries off again. So that's something you might actually use. And when I do the last night, which is going to be the forecasting night, where we go through all the different sources of weather you can look at and how to read them, we're going to deep dive into this a bit more then.
Sorry, you mean the lines need to be as far as possible? Is that what you mean?
Between here and here?
Like all the way?
You're going to phrase that question differently?
Like, so that one, like, I can see the lines a bit close, and that one's like separate.
Yeah, so this is just representing how moist the air is.
Yeah.
So there's the actual air temperature and the humidity level. So if the temperature and the humidity match, you're at dew point, and the clouds will form. If the humidity is low but the temperature is warm, this air would have to cool all the way down to 5 degrees before it would form cloud. So that's just representing If the blue line meets the red line, you're likely to get cloud or moisture coming out of the air. If they're far apart, the temperature is much warmer than dew point, you won't be getting clouds forming.
You might want to talk about that black line to explain the cloud effect.
Yeah, this is an indication on the chart of where they predict cloud to form. So down the left here, it corresponds. There's likely to be cloud at those heights, which is also where the dew points meet the temperature. And there's another good chance here where it's still touching, but then there's not much chance of cloud, which is matching the area where the dew point's far away from the temperature. Over here, these lines never meet. It doesn't predict there to be any cloud. Doesn't mean there won't be cloud.
Higher up.
Forecasts in real life are always so-so. They're never exact.
There's a serious really high up.
Yeah, we've got the cirrus cloud stuff coming up in the next bit. So it's 8:30. I've probably got about half an hour left. Is everyone okay?
Yep.
Cool. So thermals. Thermals look very different in real life. They don't just go up in a nice tall vertical column. They go all over the place. In no wind scenario, they'll generally raise above the air. We like to use our tennis court tonight. Air float up. Sometimes clouds form on them. In the middle, this is a cross section. You'll get the strongest lift generally in the core of these. And on the outside, you'll start feeling little downdrafts. So if you're flying along and you go, oh, I'm sinking, somewhere around you will likely be a thermal going up, and you're flying through the side of it. If you fly left and you get nothing, go back and fly right, and maybe you'll find the thermal. But the wind generally affects these things, but the thermal will generally flow with the wind. So say you've got the tennis court here, the wind's blowing over it, the thermal will still rise, but it'll just drift downwind a bit. Now, the air flowing into this thermal will mix, and you'll get this going on in the front edge where the leading ahead of it in the wind, the air will go up with the thermal as it's colliding and being pulled up, and then you only get the downdraft behind it. And where the lift is strongest is generally upwind. So it looks a little bit like this. There's a cross-section from above. The people flying at the front of the thermal will find the best lift. So if you think about the thermal lifting, the strongest air is going to go straight up the fastest, as opposed to the cooler air, which rises slower, will carry on downwind a little further and not be as strong. So you'll find the strongest parts of the lift into wind. So if you're flying in circles and you find yourself drifting and you find the thermal getting a bit weak, just fly upwind a little bit. You might find yourself back in the core, the strongest part of that thermal. So yeah, thermals go with the wind. Happy? Triggers. We talked about triggers a little bit, so can anybody tell me what they think a trigger is?
Well, word, or in particular this one.
Yeah, so we looked at cars being a trigger of a thermal, can trigger them off.
Which?
Yeah, so a trigger is basically anything that can trigger that thermal to lift off. So we've said cars. What other examples of some triggers? There was a cool one before.
Tennis court.
Tennis court is the source of the thermal. What triggers it to separate? Yeah.
To play on it.
Oh, water? Something cold?
Yeah.
Like,
Yeah.
Cold air coming in and mixing it up.
Like from the glacier.
Yep. Yep. Tractors driving through a field can be a trigger. But there's a few other abstract answers to this, where you can turn a katabatic wind into a thermal. Anabatic. Ana goes up. I got that backwards. Sorry. So this is some other examples of triggers. Now, this is my beautiful artwork, conducted at 36,000 feet, somewhere between here and Melbourne. So these are two separate examples. So we'll just look at the first one on the left here. So say this is our mountainside. That's dirt. That's a tree. Quite a good tree, I reckon. And this is a bit of gravel. Say there's a slip on the hill. You've got a bit of exposed gravel. The sun is going to heat this up much better than this. That's going to cause air to start flowing up the gravel. But it can't just lift straight up because there's nothing on this side to replace it. So it's stuck on the ground and it will slide up the hill, causing an anabatic airflow. Eventually it's going to reach the top of that slip. There might be a row of trees along the top of that slip. They're going to work essentially like a ski ramp. Force that air up and away from the ground, and it gives air from the other side an opportunity to come in underneath it. That lift can now rise away from the ground. As it rises, it also starts to expand. Remember, a bubble, air parcel rising will expand as it goes up, so that thermal will grow up in like a cone as well as it goes up. This example over here, kind of similar, but in this example, we have our hot rock on the hillside. It's been sitting in the sun all day, it's got really hot. You've also got a bit of heat coming up from below. The point that it separates, the trigger point, is the point on the slope where the air can get in behind it. That point, where the cross is the trigger point. So the thermal stuck to the ground up to the trigger point where the air can finally get in behind it, it's going to go up, away from the hillside. If it didn't have a trigger point where it gets lifted or allows air in behind it, it would just continue to slide up the hill as a nice normal anabatic wind up the hill. We've got another picture. We're now onto the big mountain side of things. So we've got the sun, once again, onto my beautiful mountain. This mountain has, in this example, 2 triggers. So the first one, similar to before, the sun's heating up our nice big hillside. It's got an anabatic flow of air sliding up the hill, but it can't get off because air can't get in behind. But say we get to the top of this ridge and it flattens off a little bit. Just like this, it shallows off. Now the air from here can start to come in behind. And up she goes. So one of the things you're looking for in this scenario is these triangular hills. They're a nice little thing to try and look for. If you can see a nice sort of pyramid shape, the air will converge all the way up these hills until they get to a point where it either shallows off or it becomes the entire top of the mountain. Once the air can get in behind it, you'll find the lift coming off the top of that point where it's converged and now allowed itself to separate. So the trigger point is that point of that where it starts to shallow off. Is everyone following along with that so far? Cool.
Well, actually, the previous slide, sorry, can you just go over the one with the trees and
Yeah, sure.
why the trigger point happens there?
So there's no longer anabatic flow coming up here because this hasn't heated up because it's got trees on it.
Yeah.
Also, the air sliding up collides with the tree and gets full, like it sort of acts like a ski ramp in a way.
Gotcha.
So the air hitting that. So you'll find it. I noticed a little bit
where's
here.
The air so the air can still come behind it to create the.
Yeah. So this air here is not sliding up the hill. It's just sitting there. So as it collides,
Oh yeah.
that semi-stationary air here can fill in from behind and allow it to start going up.
That's why I said on the other side it was no rock, but on the top it would just keep going up the slope.
Yeah.
Yeah, but yeah, okay. Yeah, it makes sense now.
Anywhere where you think air can get behind, it can separate. Now, real life, it won't always separate. There's a million factors that dictate this. This is just a rough idea, okay? Yeah, and...
You haven't signed this masterpiece.
Yeah, did you notice I signed that one? I don't want anyone stealing it. Good spotting. Yeah, so the tops of mountain peaks are excellent thermals because as all the air from all the sides converge on it, it's no longer stuck to anything. It's just going to keep going up.
Does that also make it hard to know which way to launch? When you've got,
Yeah, well,
like, that and rotor and wind and.
you'll quite often find you're going to get lift on your sunny side of the hill. So if you're like, okay, I'm dead serious, I want to start a cross country today, you might walk up this mountain, call it Coronet Peak in Queenstown. You walk to the summit. The sun is going to be heating up the northern side. You're not going to launch into the lead because you're just going to find no thermal lift and possibly a bit of a sink. Yeah. Everyone's favourite bit. Hello.
This is my favourite part. But really quickly, is it possible to get, so at that peak, for example, you have like the thermal, is it also possible to have the other air coming this way to create rotors?
The rotor? Yeah.
Well, he said things.
The artwork continues. Just because you asked, we're going to go into this. This is trying to make sense of why Coronet Peak works all the time in Queenstown. Coronet Peak is a lee side lift site, which makes not a lot of sense. So imagine this is the north, the sun's hitting the back of Coronet Peak from the north, but here's the basin of Queenstown. But people fly here all day long, they stay afloat. So what is happening? The sun's heating this side of it, but it's also heating this side of it. You also can get a bit of wind moving through the area. Air can be going up and then coming back down the other side. Where the wind's coming over, you might get a rotor. If there's no wind, you're much less likely to get a rotor. There's a lake in Queenstown. You'll get a sea breeze effect off a lake. You'll get a sea breeze effect off almost any water, anywhere. If you've got an object that's hot next to a cold object that's cold, you'll start to get the cycle going on. So the sun doesn't heat the water, but the sun does an excellent job of heating the land. You start getting a sea breeze. You start getting a big cycle. Eventually that cycle is going to get big enough that it starts to push up the other side of the mountain. So you get essentially a sea breeze rotation pushing up the back of Coronet Peak, the sun coming up this side of Coronet Peak. But for some reason you can never launch from here and get over the top. And that's normally because there's a bit of airflow over the top. It just comes back down and stops it. So there's a whole lot of stuff going on in real life. You get the sun causing thermals, you get the wind going up and over causing a little bit of rotor. You can get some local effects in the lee causing a bit of air to flow up. You might get some areas you can fly. You might get some areas you can't. That's a bit of more of a real life example, if that helps. Some of you? Cool. Clouds. We're very nearly at the end. So this is just a bunch of terminology and a little bit of the dangerous looking clouds you want to stay away from. So, as I mentioned before, there's two names of clouds. We already mentioned that one. Cumuliform cloud. Can anyone tell me what this kind of cloud's called? You all read that really fast, huh?
You can still read over your hand.
Yeah, good. So, these are the two primary categories of cloud, okay? Cumulus cloud, stratiform cloud. Clump, layer. Cool? Every other derivative of cloud is generally, whether it's high, it's low, it's wet, it's doing this, it's doing that, but they're all generally breakdowns of these two different kinds. This kind of cloud, the cumulus cloud, we talked about it before. Where do we most commonly find this type of cloud? Thermally lifted air. Air comes up, it's rising here, but it's not there. This kind of cloud, there's a word we used earlier, it started with O. Orographic. Stratiform cloud is normally, in most situations, orographically lifted air, but you also get it with the passage of fronts and a million other things, but that's just the most common kind of cloud we find. Here is about half of the other kinds of clouds you might ever find yourself using. Mm-hmm. So we're just going to go through the terminologies and what they mean here. Nimbostratus. So stratus, layer, everywhere. Mm-hmm. Anyone want to an attempt at what nimbo refers to?
Rain.
Yeah. Really wet cloud. So air that's rising, as it continues to condense out, as it gets colder, moisture comes out, it fills itself up with air, with moisture. It's going to get really dark, get a purpley look. Sometimes it hasn't rained yet. we get the nimbostratus cloud. Most common here in Christchurch during the easterly, like today. With a big sheet of dark, nasty, moist cloud. Nimbostratus. Here's regular stratus cloud, regular cumulus cloud. Sometimes you get a bit of a mixture. Sometimes you get a layer of clumps. Stratocumulus. Cumulonimbus. So we had nimbostratus. Now we've got cumulonimbus. Don't ask me why it's at each end of the word. Really big wet clouds. Do you remember we talked about that runaway cloud earlier? That's generally these things. As it goes up, keeps making water come out. It's going to start raining. It's going to get dark, but it's a cumulus cloud. It's a clump cloud instead of a layer. Now these words alto and cirro refer to different altitudes that the clouds form. The alto cumulus clouds, you don't need to know this. Technically, it's between 6,500 feet, 23,000 feet. Generally, these clouds are wet, but they haven't gotten so cold they've turned into ice yet. If they're really high, they're going to be really cold, and that moisture is going to turn into ice. So those clouds that the jets are flying through are literally tiny little ice particles. They glitter in the sun like glitter, and they literally look like ice as you fly through them. We call those cirrus clouds. So when you see these wisps in the air, you'll see them really high just before weather systems start to arrive. They're cirrus clouds. They're frozen clouds way up.
Like on that picture behind you.
Yeah. As opposed, and these are just like the clouds on the ground, but we call them altostratus and altocumulus, and that just means they're high clouds, but they're exactly the same.
What causes the altocumulus clouds? Because they're above where you get thunder, right?
Yeah, so say you've got air going over a mountaintop. That's one reason. Another one could just be a front. So a front is a big chunk of cold air from somewhere else making its way into the area. If it's cold, it's going to lift. It's going to slide underneath the air that was there and lift it. Sometimes that air that's lifting can be happening above 6,500 feet. It's going to start forming cloud up high. Warm cloud. So warm fronts will slide nice and easily over the top of the air that's already there, but the cold fronts come and barge in underneath. So those warm fronts cause these nice stratus layers that nicely slide up and over. Normally these cumulus clouds are caused by cold fronts that have forced their way underneath and pushed everything up, and you get those big bubbles. Yeah.
For Theo, are we looking for high cumulus or low cumulus?
To be helpful for us?
Yeah.
Depends on how high you want to fly. If you see a bunch of cumulus low to the ground, you'll know you've got lift under those, but only up until about the tops of those cumulus. If you see these up here, you might have nice, clear blue thermals up until this point, and then these ones might be forming on the top of them further up. So if you see cumulus clouds, by definition, they're down low, you're going to have low thermals. On nice hot days where the thermals are going really high, you'll get the altocumulus clouds on top. They look exactly the same, they're just given a different definition. Any other questions? Cool. Yeah?
I was just thinking about a time when I was speaking, there was like an inversion, and then as it started to heat up, there was just like, I guess like thermal pockets, just like clouds just popping up everywhere. And that's just, I don't know, I'm asking you to be honest with you, but I'm just trying to think about where that fits in here, like, and whether that's something you should be flying in. And
yeah, so
like when the sun's burning off the clouds and it's all lifting and looking a bit crazy in the sky.
Yeah, so an inversion is air getting colder, well, as it goes, getting warmer as you go up.
Yeah.
So normally we saw, imagine this is the chart from before, the air, as you went higher, it got colder and colder and colder. Mm-hmm. An inversion is the air getting warmer and warmer and warmer, and then it gets colder and colder and colder. Mm-hmm. Air won't lift until above that point, but eventually parts of the air under the inversion will start to heat up and start to escape through the inversion, but it happens later in the day once enough energy gets to the ground that it can burst all the way through. We'll go more into that when we do the forecasting night. We'll see a whole lot of inversions and stuff. Dangerous clouds. So the next is just a bunch of dangerous situations you want to stay with. Ross mentioned these earlier. Lenticular clouds. Can anyone remind us when we experience these kind of clouds? high wind and mountain waves. If you see cap clouds, Queenstown's or the mountains and other examples, you can be flying in perfectly safe air. And then you might spot down the far end of the valley, one of these starting to form, you know there's a weather system arriving. The weather that you were flying ahead of has finally started to arrive. Start thinking about calling it a day. You can be, 50 kilometres from these things and be perfectly safe for a while. But eventually that weather will reach you. Nimbostratus is just a picture of it. Anyone want to give us some examples of dangers that can arise if you start seeing yourself near a nimbostratus cloud or a cumulonimbus? Yes, you don't want to get your wings wet. That can cause them to become heavy, lots of drag, start stalling your wing. Not a good situation. Yes, wet clouds are normally powerful clouds. They start to self-sustain and you can get sucked in. Usually associated with areas of widespread lift. I don't know if any of you have ever been stuck in the sky yet, but when you get widespread lift, it can be very hard to get down. If you're near these things, you might find yourself in that situation where all the air is rising. It's very hard to get back down again. The towering cumulonimbus. Yeah. We've all seen a thunderstorm at some point in our lives. There's a lot going on in here. So this is what I fly at work, the Airbus A320. We are required to stay 20 nautical miles from these things. We don't go near them. They will rip our wings off. Stay away from them in your paragliding. You've heard those stories of people getting sucked in, passing out. Some of them die, some of them wake up in trees. These are what did that to them. If you see these around, it doesn't mean stop flying, but if they are getting near you, definitely stop flying. If they're over on the mountains over there, they might just be over there. There might just be thermals over on the mountains. The mountains might be causing them to trigger. It doesn't mean stop flying, but if they're coming towards you or near you, definitely stop flying. So we'll look at why.
How do you tell if that's a cumulonimbus? Because if you're in the air, you can't see above you. Like, what if it just, maybe it's huge, and you're like, oh, that's obviously one, but I don't know.
That's why you want to look at forecasts before you go flying. You want to sort of
sun you've got left on the ground when you fly. If you get no more sun patches on the ground, it's filling up above that. There's no more chance of the sunlight to hit the ground. That's a chance. It's something you need to watch for.
And they're really black.
If it's suddenly too easy to go up everywhere, it's too much power.
Yeah, everyone who was at Cheeseman that day, it started off as a sunny day, everything got bubbly, then it all got kind of dark at the end of the day. You don't have a choice in the matter. So what's going on is it started off as just a bit of ground that got really hot. It sent a bit of air up and it allowed it to start running away on itself. As it starts to run away, it starts to self-sustain. That temperature difference inside this cloud, it's still really warm in the middle because it's pouring so much water out. It's going to cause, some of people refer to it as a turbo effect, where that cloud starts to suck air in itself. It's now self-sustaining. Air will getting pulled into the middle. It goes up. You start getting the rotation motion. Coriolis effect, just like in your toilet, air going up starts to rotate. You start getting the tornado forming underneath. Sometimes it hits the ground, sometimes it doesn't, but in the centre of every towering cumulus is a tornado that just hasn't hit the ground yet. Terrible things to fly through. Trust me. A couple of them by accident. I've had computers knocked out of systems, things unplugged themselves in airplanes and had like half the cockpit go black. It's not a good time. These things can rise all the way up to what we call the chopper pause, the point in the atmosphere where you've gotten so high that the air actually starts to heat up again. It can't go any higher because as the air gets higher, it eventually does reach this point, an isothermic layer. It stays one temperature and then it starts to warm up as you head up into the upper atmosphere. Nothing gets above that because it's actually warmer in the upper part of the atmosphere. So it goes all the way up to that point. We fly our jets just above that point where we can avoid all these things, but we can't always. as these things move with the wind, because now they're self-sustaining, they don't need the heat source, they can bugger off, go where they like. Ahead of them you get big downdrafts. So all of this air going up has made a whole lot of moisture come out. All that moisture gets really heavy, all that raindrop, it all starts to fall. Well, that rain will start to pull air back down with it as it starts to fall. So it goes up, it falls out the top, it starts to descend, and you get these big downdrafts ahead of it. And then all of a sudden, you've got what we call a microburst coming out the front. You've got this huge downdraft just ahead of this thing, pushing down and out. So not only is the updraft and the suck dangerous, but also the downdraft and the push out. It's all crazy wind speeds that airplanes stay away from. So all of that's going on. Just stay away from these things. You'll survive. If you're near them and you can't get out of them, yeah, I'm not the person for advice.
So that's what becomes the dust front.
Yes.
Yeah.
Yeah, it's generally up here hail and down here rain, pulling it all back down again ahead of the thing as it moves along. So the dangerous things being the convergence, the tornado, the rain, the hail, how high it goes you can't breathe, the area it will cover, and the microburst in front of it. Enough said, just stay away from it. Cool. Fog. Innocent little fog. Has anyone landed with the fog around out here yet? Fog's really innocent. But what's dangerous about fog is just after sunrise, the fog will mix and generally get thick before it goes away. So fog is caused by, on a clear night, all the air touching the ground getting really cold. The earth cools down in the night, there's no sun on it. Eventually it gets so cold it starts cooling down the air above it. That air might get cooled below dew point. The fog starts to form above it. Does that make sense? Now as the sun finally hits that air in the morning, it's going to start warming things up, start mixing things around. That fog doesn't just get sucked back in. Normally it gets mixed up a bit, becomes a little bit thicker, and then it dissipates. Now if you're taking off at sunrise and you go, there's just a little bit of fog down at Ferrymead Park, it's about an 8-minute flight down there, trim speed, straight line. 8 minutes, that paddock might completely disappear on you. So just be aware. If you're ever taken off above fog, just look at it and go, is it going to stay the way it looks right now when I'm there landing in it? Not much to take away from that, but just be aware. Fog's not as innocent as you think. If it's big enough to hide this bridge, it's big enough to hide your landing. Fog you can see straight down through to the ground about this far until it gets that thick and then you can't see straight down, let alone on an angle. You definitely can't see much at all. Big picture stuff. We kind of went into this during the last brief, but it's just a bit of an awareness thing. The atmosphere does consist of a bunch of big rotating cells. Air goes up at the equator where it's the hottest, and it sinks at the poles where it's really cold, right? And you get these big rotating cells where air is just replacing itself like a sea breeze. Air goes up at the equator, it comes back down, and in the middle you get a bit of a rotation, and it's a bit of a result of these other two cells rotating. When someone refers to something as a jet stream, we're talking about columns of air that flow really fast in the upper atmosphere. These things generally happen sort of above 30,000 feet, so you're not going to find yourself near them. And they just follow these two little meeting points. So you just get a bit of hot air, warm air here, mixing with slightly cooler air here. They arrive together, the hot air goes on top, things start to rotate. And as you rotate, everything starts to spin in funny directions. Air going up will spin that way, air descending spins that way. Down the middle, you get a jet of air flowing along it. We call that the jet stream. You won't ever have to worry about the jet stream as a paraglider pilot. It's something that happens in the upper atmosphere, but I've just put it in here so you're aware of it. Someone goes, watch out for the jet stream. You won't be anywhere near the jet stream. but it is an atmospheric river of air in the upper atmosphere moving around the planet. It is generally what causes all the highs and lows. Air comes out of a jet stream, causes a high, goes into a jet stream, causes a low. They're very important. Don't worry about it tonight. And the last is sort of the passage of fronts. We're at about 2 slides left before this thing ends, so we can call it a night. 9 o'clock. So we all know that we get fronts in New Zealand. What you might not know is there's a cycle to them. And this is what they look like here. So these waves go up and down, and they rotate around the planet. During different times of year, these fronts are caused by the cold air descending over Antarctica here and pushing outwards. During the winter, it's really cold. And it's going to push out a lot harder off the Antarctic. And you're going to get these fronts coming up and over New Zealand. During the hot months, it settles down a bit. You don't get these pushing out. You get a lot less fronts in summertime. The shoulder seasons, autumn and spring, where it's heating up and cooling down, you get the most of these fronts because it's cycling a lot, trying to find balance. And you get these fronts hitting you. So it's just something to be aware of as a pilot. When you're flying in those shoulder seasons, you're going to have yourself a lot less days where you can fly because of these fronts. And there is something you can look up if you want to get enthusiastic about it. There's an index. It's published online on the Met Service. It'll tell you how common these are at the moment. If you want to plan your trips ahead of time, you go, what part of the year can I start planning these trips? You can start watching the forecast of these indexes when these fronts are going to start coming. So this is just something to be aware of. It's not really relevant to your day-to-day flying. This is just to so you know. And the second to last slide, we already talked about what a front is. This is what a front looks like on a piece of paper. Cold front, warm front, occluded front. Has anyone here not heard of an occluded front? Cool. So what you've got, a cold front is just an area of cold air being pushed into a region that was warmer. Along the leading edge of it, you get a cold front. As it slides underneath, it's going to push air up and cause a bit of rain and a bit of cloud. Same with a warm front, but the warm front will try and slide up onto the top of the air that was already there. And you get those stratiform clouds up high. But if you get them meeting together, so you've got air that was already there, then you've got cold air sliding underneath and warm air sliding on top, you get kind of a triple-decker sandwich. We call that an occluded front. They're all in the same place. Very wet kind of place. That's the takeaway from that. This is what it looks like on what we call a synoptic chart. If those of you that grew up in New Zealand, they used to have these on the news every night. They'd play the synoptic chart. So you've got the low, the high, and these big fronts that normally cycle into the low. So we had cold air from here rotating around this way, bit of warm air that was there rotating this way, and then they're mixing together into the low and causing a bit of rain. So if you're looking at these, the takeaway is cold area, a lot of rain, warm area, more rain, whole lot of rain. Cool? I'm not going to deep dive into this. I just wanted you guys to see this stuff and be introduced to it.
Sorry, can they suddenly change directions?
Yeah, so they normally just rotate around lows. So they will flow kind of like that.
Can they go like...
Like randomly do that?
Yeah.
No, they'll move with the low pressure system. And they generally sort of trend in a generally the same direction, but they do rotate around. This is a bit of a cross section of a front. So, the top we have the cold front, on the bottom we have the warm front. So remember I talked about the cold front, the cold air always tries to go underneath. And as it does that, it looks a bit like this. So it's flowing into this area, this bubble extends in, and as it arrives, it rapidly pushes all the air that was there up onto the top of itself. You get those cumulus clouds, you get towering cumulus as this area all gets forced up. As opposed to the warm air, it doesn't have to push that air that was there away. It just slides up onto the top and you get these widespread stratiform clouds. Sometimes nimbostratus clouds. If it gets high around here, you get the altostratus cloud, and right up ahead of it, where it's frozen, remember the name of those? Cirrostratus cloud, sometimes cirrocumulus. You just piece them all together depending on what you're looking at. There's about 1 billion more sub-definitions of all of these. We're not going there. So that's just what you can expect. If you get a cold front, expect there to be really rapid clouds exploding. But generally, once you get to about this part, it all settles down really fast. But when you get those drawn-out rainy days that just go on forever, that's normally a warm front because it takes its time doing its thing. You get widespread rain. And this is, if you're looking at windy, what a front will look like. There's no spiky blue line or anything. But it's just a bit of a wind shift, and then along the frontal edge it has a little bit of a kink in it, with a bit of moisture showing where it's raining as it's pushing up. So that's what a front will look like in a system you might actually find yourself looking at. If you see that coming past, you don't want to be flying while this thing comes past. But behind it, nice clear air. Sun will come through, hot rock, cool and cold air, you might get some nice lift. Ahead of it, you notice here it's really windy. Ahead of a front, it's always windy. It's one of those rules. It's to do with the pressure changing. As that thing comes past, it accelerates the air. So if you're flying here, and then all of a sudden the wind swings around to the north really fast, it gets really strong, you're just about to have your front arrive. Go land. It might only take a couple hours, and it might be nice behind it again. That's it. We got to the end. Congratulations. It's only just past 9 o'clock.
Thank you.
If anyone has any questions that are like completely off topic, feel free to message me. But there's going to be a final night. Basically, the goal of the final night is to go into all the places you can get weather from and just see what's there, show you what you're looking at, explain what you're looking at, so you can actually go out on your own and sort of see what's coming. Start making decisions before you go flying, because you always want to check the forecast before you go flying, and it's not just where the wind's coming from. Will there be rain? Will there be fronts? Will there be mountain waves? You can find all that out. So when we do this last night, we're just going to go find all the weather.
Are you going to post your artwork in the form of your presentation on the...
Only the one that I've signed, so you can't steal it.
Copyright.
I don't think we'll be making much money off that artwork.
No. If you do want to go into the detail again, the Met service, Met briefing for PPL pilots is the best place to go to. It's free and it's pretty good. If you want to pay for commercial pilot training, there's a book series called Waypoints, really good for training pilots about the weather, but they're expensive. Otherwise, don't be scared to ask people on the chat group as well. Everyone's terrified of asking weather questions and site questions on our community chat. Just ask them. Everybody loves being a know-it-all.
Is there any chance that the last two can be uploaded so that we can? I just want to go home and recap and do this in my own time. So is that?
If you guys want this PowerPoint, private message me on WhatsApp. I'm not going to post it on the chat because it's like 30-something megabytes. It won't email. I've got to send you the link to a Google thingy to download it. But just private message me and I'll just send you what you need.
Could just be like the artwork bits, because it's that. It might be confused for transport, but it's actually really valuable.
Yeah.
Thank you so much. That's really helpful.
No worries, guys. All right.